make a little speech. And dear friend and participant of Icsmartgrid video conference, it is with real emotion and joy that I have the honor of chairing this 80th International Conference on Smart Grid, which will be historically marked by the consequences of the COVID-19 pandemic. For many of us, it is the first time that this type of event has been held, and I hope that our work will be crowned with great success thanks to the recognized high quality of scientific communication. Unfortunately, we will not have the convivial moments of sharing that usually accompany our conference. I think we will have the opportunity to meet again in another city in a context of better global health conditions. I must first of all thank Professor Kolak and Professor Kurokova for once again choosing the city of Paris and myself to chair the conference. For this conference to take place, it required a real tenacity and very great skill. On behalf of all of us, I congratulate and thank Professor Kolak and his team for having accomplished such a feat in such a short period of time. To be honest, all the credit for the realization of these events goes to them. I have a thought for my young colleague, Dr. Amadou Tankari, who was very much involved in the preparation of the conference in the city of Paris, but whose efforts were undermined by this unprecedented pandemic situation. I would particularly like to thank the eminent specialists who have agreed to deliver keynotes and thus contribute to the influence of our conference. My special thanks go to Professor Hissel from Belfort and Professor Al-Said from Grenoble for having responded favorably to my very late request. I won't be long, and I wish everyone an excellent conference. Thank you.
Thank you very much, Professor. Thank you.
Okay. Thank you very much, Professor Brahima. And now I would like to invite Professor Kurokawa to deliver his speech to our audience.
Yeah.
Please, Professor Kurokawa.
Thank you very much, Mr. Chairman. Yeah. So, good morning, ladies and gentlemen. It is with great pleasure that we welcome you to the Icsmartgrid 2020 in Paris, France. Smart grid technology really can create a wonderful future society. I hope that this conference will provide you with the opportunity to encounter very exciting innovations and ideas to this field, although this conference is online style due to COVID-19 influence. By the way, the Icsmartgrid invite Team Mike as a diamond sponsor. Mr. Hidehiko Chi, Corporate Senior Executive Vice President, support as a honorary chair, and Mr. Akira Kawaguchi, Vice President, will speak as a second keynote speaker today. We appreciate their support for the smart grid field and our colleagues. Finally, I wish you a pleasant, productive, and creative time to develop a new technology in this conference. Thank you very much for attending Icsmartgrid. Thank you very much.
Dear Professor Kurukawa, we thank to you for your prestigious speech. Dear Matsui, would you like to continue? Where is Matsui? I can't see. Yeah, please. Or shall I continue?
Okay.
Okay. Okay, I will continue.
Yes.
Uh, uh, Now, I would like to invite Professor Polak to deliver his speech. You know, this is great experience actually. In one side of the world is morning and in the midday and midnight. So I would thank all the participation around the world. It's wonderful picture of Icsmartgrid. So please continue, Professor Polak.
Good morning to everybody from Istanbul in Turkey. And I know some part of the world is now in midnight, like USA, Adele is there, and some part is still evening. And this is the benefit of the technology brings us together at a time, regardless of time difference all over the world. So I'm very happy to be with you in here. I see smart grid, the worldwide known conference and supported technically by the IEEE Industry Electronic Society and Industry Education Society. Year by year, its quality and the level is going up and up by your contributions. Last year, you know, we were in Australia. In 2018, we were in Nagasaki in Japan. Before that, we organized this one several times in Istanbul and Antalya and other places. So up to now, we publish very good, high quality papers at this conference. This year, we have 5 keynote speakers, 3 tutorials, and 33 high quality papers. After saying this, I would like to send my great thanks to Teammate, who supports our conference financially as a diamond sponsor. You know, this year the tuition fees have been halved because of this pandemic. Nobody is traveling, and then we are also not allowed our companies and our governments to go out. So everybody is staying at home and then trying to carry on their business on the computer. So therefore, we ask this situation to IEEE what is going to do, how we will organize this one. They said it's up to organizing committee, and then if the organizing committee wishes, you can organize it in digital platform. So we ask this question to everybody registered on the system. You know, we have more than 1,200 registered members on our website. So we ask this question to everybody. Majority of the people said, okay, we can organize this conference in digital platform. Therefore, we decided to go on, and then instead of canceling or postponing the conference, it is better to have it on time, because we don't know in the future what will happen. Still, the pandemic, COVID-19 is very high all over the world, and then people are hesitating. So therefore, I think we are in the right path to do this conference on time. This year, we have received 57 submissions from 25 different countries, and the committee assigned at least 3 reviewers for each paper. And as a result of the reviewer comments, we have accepted only 33 papers. And that means our acceptance rate is 58%. So 58% acceptance rate for this conference is really very good rate. And you will see during these 3 days time, all the papers are very high quality. And I have contacted yesterday almost all the presenters of this paper, and I asked their phone numbers and the other contact address in case they are not connected. I will call them. So they are ready to present the papers during these 3 days. Of course, this conference cannot be carried on without your great support. The organizing committee is working very hard, and they are supporting our high quality conference every year. Therefore, I would like to thank to, first of all, the General Chair Brahim Dakyo, Professor Brahim Dakyo, the General Co-Chair Professor Fujio Kurokawa, and the other committee members, especially the Professor Ramazan Binder, Şeref Saguroğlu, Matsui, Professor Matsui, Bülbül, and other colleagues. Of course, I would like to send my great thanks to Professor Adel Nasiri. He is in the middle of the night now waiting for us to deliver his good speech. And we feel his support every time. And then I hope in the future we will organize one of these conferences in USA again, and we will get his support more. Now, I think it's almost time to start the first keynote speaker, and therefore I would like to give you some remarks during what we are going to do during this conference. First of all, we have almost 40 attendees now. I kindly request all the attendees to close the microphones. Whenever they want to ask a question or talk to us, they can open the microphone, but the camera will be open all the day. And we are also recording all the speech in here, and maybe you are recognized on the screen, it is recorded. So whatever we are talking here, and they are all recorded. And we will share this information with the IEEE later on. Because this is very important, what we are doing here on behalf of the other societies, industry, electronic and industry application societies. So we have to be very careful, and what we are doing in here should be very high quality. Therefore, this is a very scientific meeting, and we will listen to the speakers, and then we will be given a question time. At that time, you can raise your questions. So this is first thing, and the second thing, if you have any other questions, you can call me or send me a message by email or WhatsApp. I share with you. And last thing, you know, after the conference, we will send all papers, files to IEEE. Therefore, one of you open the microphone now. I closed it. After the conference, I request you to upload your final camera-ready version of your paper immediately. We will check these papers and then look at their similarity ratio by using the Authenticate software. If the similarity ratio is higher than 20%, we will send it to the authors and ask them to reduce the similarity ratio. Then we will open the copyright form section on the website, and then we will ask you to fill in the copyright, IEEE copyright forms. Last year, some of the paper were not presented at the conference, and then we opened the copyright form earlier. They filled in this one early, but later on they didn't show up. Therefore, we had a little bit problem. Therefore, we have not opened the IEEE copyright section yet. It will be open after your presentation. Today, after each presentation in each session, Professor Ramazan Binder will share the attendance certificate on the screen that can be downloaded or copied by everybody. But right after that, Professor Ramazan Binder will send this attending certificate to the person's personal email address. So that means everybody will receive their attendance certificate after presentation. Thank you for your listening to my speech. I think it's not too long. Now we can start the keynote session, Mr. Chair. Thank you.
Okay, dear Professor Kolak, we would like to thank you for your introductory information and opening speech. And Matthew, would you like to tell something, or we can close this session and start with invited speaker session?
Yes, please close.
Okay. Dear General Chair and co-chairs, we would like to thank you for your opening speech, and we are hoping and wishing that this conference will be very fruitful for the participants, for the attendees, for everybody, and hope it helped us to handle this pandemic term successfully. Okay, thank you very much for your, I am applauding it, okay? So now we would like to invite the other session chairs, Professor Halil İbrahim Bülbül and Professor Rosario Micheli, and now their turn, please. Dear
Okay, Michele is not in. I think I will invite him, but for the time being, Professor Bülbül, you can carry on.
Okay.
There is another conference, you know.
Okay, thank you. Thank you very much. I would like to thanks firstly for the conference organization, for the conference chair, Professor Daima and Professor Kurukova and Professor Kolak. I am hoping that it will be a successful conference in this year because of the pandemic. Hope we will recover the next year, whatever we will missing something. I would like to invite the first keynote speaker. Also, before inviting, I would like to give some information about him. Professor Adel Nasiri, he is in University of Wisconsin-Milwaukee. Dr. Nasiri is presently the Richard Ray Greek Chair Professor and Director of the Center for Sustainable Electrical Energy System and College of Engineering and Applied Science at the University of Wisconsin-Milwaukee. He is also a site director for NSF IUCRC on Grid Connected Power Electronic System. Dr. Nasiri served as Associate Dean for the Research of the Engineering in 1915 to 1918 and was the founding director of the UWM Connected System Institute in 2018 to 2019 at UWM. His research interests are renewable energy interface, energy storage, and microgrids. He has served as the primary investigator on several federal and industry-funded research projects. Dr. Nasiri has published numerous technical journals and conferences papers, and related topics. He is co-author of two books, several books, chapter, and holds 7 patient disclosure. I would like to stop because he has a very long background. I just want to invite him for his speech. Dr. Nasiri, it's your turn, please.
Thank you very much, Professor Ibrahim Bolbol. I really appreciate it. Good morning and good afternoon to everyone who's listening. I would like to thank the conference chairs for inviting me and having me, and really appreciate every one of you listening. So I am sharing my screen. I want to just do a quick check. Professor Bolbol, do you see my screen?
We can see it clearly.
Okay,
yes,
perfect.
it's okay.
And I'm going to just put it in presentation mode. So I just one quick check is I tried to see if the chat box is working for any questions that you might have that you could send through chat box, but I didn't see it activated. So what I'm going to do is I'm going to wait, kind of finish at about 10:50 a.m. So give about 10 minutes of Q&A. But if the chat box is activated, you can send your questions there, and Professor Bolbol can read the questions and we can answer. Okay. So with that, I'm gonna start the presentation. One good thing about doing it virtual is, you know, a lot of things get really more efficient, especially in terms of time. So I hope every one of you is safe and sound and healthy with your family. And due to this COVID-19, imagine it's, I would have loved to be in Paris now rather than, you know, being midnight in the US and presenting this over computer, Microsoft Teams. But I really appreciate every one of you listening to this session. So the discussion today, the first one, I want to do a deep dive into the concept of dual active bridges and how they are can be used, how they can be controlled, what their components are, and their importance to kind of concept of really a smart electrical distribution systems, and what they can provide for to enable resiliency, to enable a smart concepts, provide compactness, and a lot of benefits to electrical distribution systems. Before I start, I want to just give you a quick shot at what UWM is and what it is about and what we have here. University of Wisconsin-Milwaukee in the grants, it has right now about 27,000 students. It has a research budget of about $60 million. And it is a Research One university in the U.S. among 115 Research One universities in the country. It does have 12 schools and colleges, large and small. Engineering is not really the largest college on campus, but engineering is very active in terms of research, and engineering runs a lot of centers. And the federally funded centers include one center that I direct, which is called Grid Connected Advanced Power Electronics System Center. So UWM is located in a urban setting. City of Milwaukee is the biggest city in Wisconsin. The metro area is about 2 million people. The city is about 700,000. has about 32,000 and about $20 billion of economic output. So right in the kind of population center of Wisconsin. Our Center for Sustainable Electrical and Energy Systems, if I want to just make a quick note, please mute yourself if you are not planning to ask questions. So the center, the idea behind the center is to bring together the capabilities within UWM and the college to advance energy research and education and to do partnership with industry. And that's one of the biggest strengths of us in the College of Engineering, to work very closely with industry and research that really benefits industry. Our center has 4 faculty members, 2 visiting professors, 2 postdocs, and 25 graduate students. It works on various electrical power courses, energy conversion, power electronics, the cyber physical systems, resilient systems, and so forth. And we conduct many projects that are being supported by Department of Energy, Defense, by National Science Foundation, by Navy, and by industry. So our Center for Grid-Connected Advanced Power Electronic Systems, or GRAPES, is a center that is funded by the National Science Foundation and our industry members. The center has 2 domestic members, University of Arkansas and UWM, and 2 international centers, universities, RTWH in Aachen and Yonsei University in South Korea. It has 17 industry members in the US and many more in Germany as well as in South Korea. So with that, these are the list of projects that we conduct in the center. And kind of a really broad list, includes a smart and connected energy and water systems. This is supported by the Air Force. We have we conduct a lot of projects on compact and high power converters, like a 500 kilowatts, 2000 hertz converter. Probably I call this the most compact converter I've ever seen. It's in a 40 liter space. You do 1 megawatt of power conversion, and then we do have extremely compact energy storage converters, 100 kilowatts and above that. This is supported by National Science Foundation. Distributed microgrid controls, multi-port solid-state transformer that I will discuss in this talk, medium voltage solar PV inverter, medium voltage and low voltage isolated AC to DC converter. These 3 projects, I will just discuss them today. Then medium voltage AC and DC architectures with the Navy and cyber secure electrical distribution systems that is supported by the NSF. So one topic is, okay, why do we want to talk about the dual active bridges? I kind of introduced 4 projects here that all 4 use dual active bridges. And for a starter, this project, I've worked on this for quite several years now. It has been 3 to 4 years. It is a multi-port solid-state transformer. So most of us are familiar with the concept of solid-state transformer. Solid-state transformer replaces the low voltage or low frequency transformer and moves the isolation frequency higher. And they have been really proposed, and they have been used from frequencies from 3 kilohertz up to 100 kilohertz. And then you add from AC system, you add a rectifier. Then from rectifier, you move the frequency up to high frequency. You put a high frequency transformer, and then at the other end, you take the high frequency and then rectify it and then take it to your load. So you could see from here, for instance, this is a multi-port system, but in a one single port, what we have is, I'm trying to show the mouse here, so it doesn't come up. Okay. The medium voltage on this end, you do convert it to high frequency, and then over high frequency transformer, you can take it and you can charge the vehicle, a battery, which could be really any stationary or any different type of battery. At the same time, when you move the frequency up, the transformer really becomes much smaller. And then you add these converters that add flexibility and controls to the system. So now you can control the power as it moves up. And on the other hand, this concept of multi-port integrates several of these sources and loads in just one single system. You can have a voltage connection here, medium voltage at 4160 volts. You can have the energy storage, you can have solar PV, and you can have load. Load N could be single, one directional, of course, single directional here, but and renewable energy port can be just one way as well, but energy storage and grid, they must be bidirectional. So this is one project that at core, it uses a dual active bridge. Another project that we have been working for the past couple of years is how you can get solar PV and directly connect it to the medium voltage, and do that by getting rid of the low frequency transformer. So you go up and on the secondary of the transformer, you move the voltage up to medium voltage and then to the grid, rather than putting it at the low voltage and use it as a large transformer to get it to grid. Isolation is required, electrical isolation, so where the transformer is needed. The third project that kind of falls into the same category and then uses the same concept is when you have medium voltage grid in the US, the medium voltage, what you see on the left, the distribution voltage from grid, from utility company, the lowest voltage you get is 13,800 volts. So 13.8 kilovolts. And then how you can get that AC voltage and directly generate 1000 volt DC. And this 1000 volt DC would be at high power, and it can be used for fleet charging of electric vehicles. So you can have then vehicles there, either onboarding or off-board chargers from 1000 volt DC and charge several vehicles. And then doing that, you have isolation from the grid. And in addition to that, so you have 1000 volt, you have series input. One of the issues that we have with power electronics is that our current and voltages are not there for us to directly connect to 13.8. So that's why we are using this 11 level converter using silicon carbide devices. And then this uses 1700 volt commercial devices. And then the zoomed in version you can see on the right hand side, where we are trying to build this at the lower voltage when single phase 480 comes in, and then 400 volt DC goes out, and then there are 3 levels and you build each level. So what it really offers is isolation, mobility, control, and many other benefits that you can get from this setup. And at the core, again, you see it has a dual active bridge. The third project is moving the voltage and power for dual active bridge to the limits that we are able to do. And by that, we get the input voltage DC to 13 kilovolt DC and output voltage to 7.2 kilovolt DC. So the input, if you do that, you can connect to a single phase 13.8 kV utility voltage. At the output, you can get to the highest level of electrical distribution voltage in the US, which is 4163 phase. So at the output, you can use that, and then on the left, you can use 10 kV silicon carbide devices, which have been researched for several years. They are not commercially available, but they are being built by several universities, especially by our partner, University of Arkansas. They built 10 kilovolt switch silicon carbide devices. Then on the right-hand side, you would use 6.5 kV silicon carbide devices. The transformer is at 20 kilohertz at single phase at 670 kilowatt. And then the whole system becomes a 2 megawatt system. So we're moving the frequency, switching frequency there to 20 kilohertz, which is really pushing the limits all the way for the system. So again, this is a dual active bridge, but a three-phase, a three-level now. And we have to use three-level to meet the voltage. And so there are several dual active bridge concepts that I'm gonna discuss here. The first one, the basic one, is the dual active bridge on the top left. Then on the right-hand side is a multi-levels that you use a three-level NPC dual active bridge. Then on the bottom left, you have a triple active bridge, but you have 3 inputs to your system. And on the right-hand side, right bottom, it's a quad active bridge, which has 4 ports and then can be used for enabling nodes in microgrids, in AC/DC microgrids, or it can be used for any distribution system. Okay, so what is the basic description of a dual active bridge? So on the left-hand side, you have a bridge. On the middle, you have a high-frequency transformer. On the right-hand side, you have another active bridge. So what we do is apply voltage pulse on the primary of the transformer, and we switch the devices on the output to create 2 waveforms. The primary could be any waveform here, on the secondary could be any waveform there. So in most papers and presentation, the way you see this too is the input voltage and output voltage are the same. The duty ratio of input and output are the same and generally 50%, meaning that it's for 50% of period, the switches are these 2 are on, and the rest of the period, these 2 are on. But that case is really is kind of a special case. The more general case is that you have a duty ratio on the primary, a duty ratio on the secondary, and the voltage value on the primary and the voltage value on the secondary, and then a phase shift between these 2. So you have really 3 degrees of freedom to work with this system. And with this 3 degrees of freedom, you can get a lot of control from this system. So dual active bridge have been around for a really long time, but this concept of what we call a triple phase shift was only introduced in 2017. So then when we call a single phase shift is when you consider your duty ratios at 1, meaning that you are really at 50% full duty ratio for both signals, and you change the phase angle between the 2 sides to control power. Then in 2008, 2 authors discussed the dual phase shift, meaning you keep the phase shift as is, and then you change D1 and D2 and the duty ratio to transfer power. And then in 2017, we had the case of introducing triple phase shift. The case of very general case when you have D1 and D2 and phi all are changing. And with that comes the question, what is the best? Which D and phi is the best for the system, D1, D2, and phi? And so one concept is what the best means. So for us, we took this question in a sense that how can we transfer a specific amount of power while minimizing our RMS current through the bridge. That, of course, gives us a smaller loss in our switches, gives us a smaller loss in our transformer. So we considered that IRMS, minimizing that IRMS, be the best case for a specific power. So the task has been to make that work. So the complications that you get is this, that your near actual system for a DAB looks like this system. A simplified model is this, that most people use to look at the power transfer. And with that, your current really changes when you change voltages on each side and when you have phase shift. So your current equation is not really that simple. Another problem that you get is if you want to use first harmonic approximation for your system. A lot of people use first harmonic approximation, but there is a basic flaw with using basic and the first harmonic approximation. And what is the basic flaw? You see all these waveforms, and in this figure, all of these voltage waveform have this fundamental first harmonic voltage. So although they are very, very different, all of them, they result in this fundamental voltage. Meaning if I apply any of this on the secondary and any of this on primary first harmonic approximation, it's going to give you one result. However, the power would be way, way different. The current would be way different between primary and secondary. So that is not going to really absolutely give the solution. So we looked at a really very general approach, how we can solve this. And by that, we look at the possible combinations. So for this system, looking at all general cases, at the end, we saw that there are really, you have 1, 2, 3, 4, 5 cases, 5 specific cases that you can categorize. And then we named them front, right, left, middle, and rear in terms of power transfer. And I show you here what they look like. This is the front, left, right, middle, and rear. And then the blue one is the primary, and then the green one here is the secondary. I'm sorry, the green one is the primary, and the blue one is the secondary for the whole system. What you see in the middle layer is the current that goes from the primary to the secondary when you apply these voltages. And at the bottom layer, you see the power that flows from the left to the right. And so you can imagine that there are several formulations that you can do to get the equations for this system. And to do that, you got to find out piecewise modeling of the current and the power and then RMS current to calculate the RMS current. And this is what actually we did. For instance, I'm going to move this up here. So for the case of where we have full duty cycle 50%, and then of course there is only phase shift between primary and the secondary, the current waveform is here. You can go piecewise and look at when the voltage is positive, find what the current is in 2 steps, these 2 currents. And from there, you can calculate the RMS current when the primary voltage is positive, and then you can calculate the power. And if you calculate the power becomes a function of V1, V2, the inductance, as well as the phase shift. And it would be phi multiplied by 2 minus phi. And phi is in per unit in this case. So it becomes like almost a sinusoidal shape in relation with phi that maximizes at phi 1, and then on the other side, it just goes up and down. So this is This is very specific case. And the more general case, you would have the power for 5 different equations for power versus D1 and D2 and phi as well. So for all the 5 cases, you would have 5 different cases. And the same is true for the RMS current. And RMS current equations are already much more complex. The I comment that you see on the top right is an element for RMS current for every case that we have. So you can calculate the RMS current for each case, and you can formulate it, what it is. And with that, you can definitely apply Lagrange equation. And doing a Lagrange, you want to minimize the RMS current versus D1, D2, and phi. And with that, the first equation that you get is this. The best case would be if you have D1, V1 is the same as D2, V2. Meaning if you have a voltage, 2 different voltages at the input and output, you must set the duty ratio based on the voltage. That would minimize your RMS current. And in addition to that, now you have to control your angle. So there are 3 cases when you control the DAB. There are 3 zones. In the first zone, you have the ability to control D1, D2, and phi. In the second phase, or zone 2, either D1 or D2 is saturated at their full 50% or 1 per unit, and then phi changes. And in the third case, you have D1 and D2 are saturated, both of them, and phi changes. So you have 3 cases, and you have to apply Lagrange for all 3 cases. If you look at the zone 1, the arrow here shows the optimal path for the D1 and D2 and phi. And with that, you can get the equations for D1 and D2, and you can get the power versus D1, D2, and phi. So it's just actually expressed on both ends by V1 and V2 when V1 is greater than V2 and V2 is greater than V1. I'm sorry, sometimes I cannot show my mouse here on the screen. I really don't know why, but I cannot point out to the specific equation here. For zone 2, either D1 or D2 is saturated. So if V2 is less than V1, D2 is saturated. If V2 is greater than V1, D1 is saturated. And with that, you can get the equation for another one, either D1 or D2. And then you can get the equation for phi, and you can get the equation for power. One of the biggest challenges people always have is, how do I control my Ds and how I control my flux when I control a DAB? And this is the equation that gives you the minimum RMS current. And that's what we have used. You can use, of course, other objective functions here to get this working, but our objective was to minimize the RMS current. And the last case is when D1 and D2 are saturated and you only have phase angle phi to control the power. So based on the power demand, you just change the phi. And then the phase zone 3 is really a small zone. It's just shown at the end of those arrow path. Okay, so I want to just show you what happens if you optimize it and when you don't. So we did optimization for all cases, and I'm going to show that only for the case where V2 is greater than V1. So for the case, for instance, if V2 is 3 times V1, on the left-hand side is the traditional method. That in the traditional method, you have some RMS current, you change the angle, and D1 and D2 both are 1 per unit. And when you change the phi, you change the power, which is the horizontal axis here. And with that, you get some RMS current, which is the red curve here. If you do a traditional method, even at 0 power transfer, you have somewhere about 0.63 or so per unit of the RMS current. This RMS current is not doing anything, but only transferring reactive power from one side to another. it doesn't really do any good here. It's just creating loss. The current is changing really from in a small range from 0.63 all the way to 1 per unit. So although the power is changing from 0 to 1 per unit. On the right-hand side, we move it from zone 1, zone 2, and zone 3. And then doing that, we change the current, RMS current from 0. You see at the 0 power, the RMS current, which is the red curve. I'm sorry again, my mouse for some reason doesn't work here. It's the current is 0, and then the current moves all the way to 1 per unit when we have 1 per unit of power transfer. And for this case, first D1 increases and saturates, and then the D2, and then phi is after that really controls the power. So just moving from the left to the right, you get significant amount of efficiency improvement, especially at the low power, which most of the time these converters are working at their lower power. And then, of course, depending on the amount of power transfer and relationship between V1 and V2, you move from zone 1 to zone 2 to zone 3. And this really depends on the system operation. So moving from there, from a dual active bridge to a triple active bridge, here the case becomes a bit more complex. So you thought that the first case is complex. Here you have 3 duty ratios, you have 2 phase shifts, and you have 3 voltage levels. So in total, you have 8 degrees of freedom, or eight things to work on. And then from there, you want to transfer the same amount of power from one port to another, and then at the same time minimize your RMS current. So imagine this is going to be a bigger mathematical problem. And we could not solve this really manually with hand. We used MATLAB functions to parametrically solve the problem. And then for a very nominal case, when D1, D2, and D3 are 1, you can see the power equation that have been derived is based on V1, V2, and V3, and phi1 and phi2. And these are the power of the 3 ports, depending on what their voltage is and voltage level is and what the phase shifts are. So this is a very simple case. And then from there, you can move to a general case that you really get about 8 cases that you can optimize. You can have an optimized case for your system. The general cases, there are so many, but 8 of them give you a more optimized case. And for those 8 cases, you can calculate your current, you can calculate your power, and so forth. I'm just showing here mode 1 and mode 2. Where we minimize the total RMS current. Here, RMS current is originally total RMS current. And as you see, the equations are fairly complex, but they can be programmed, of course, and they can be used for this work. So this is an extension of the DAB case. The third one is a multi-level dual active bridge. And in multi-level, now for each side, you get 2 duty ratios. D1 and D2, as you see in the top figure here, and then you get different voltages, voltage level as well. So you have D1, D2, and phi, and then you have different voltage levels. And then you have to go through some simplifications here to help the system. And one of the simplification is that for the primary and secondary, you want to consider a ratio between D1 and D2. And that is really to simplify and to minimize the current rise as well. If you define a relationship between the duty ratios of the primary and the secondary, so meaning that the voltage that falls on the transformer doesn't exceed half of the DC bus. As you see here, you don't want to put the full voltage on the transformer and on the current ramp. So based on D1 and D2, you can get the primary voltage, VAB. You can get the secondary voltage, VCD, on the port B. And with that, you can see here, if you define DA1, DA2, and DB1 and DB2 for the primary and the secondary one, you can see the voltage difference on the inductor that establishes the current. And you see that in several time steps that you see here. About each half cycle takes 9 time steps. And for the case that when we consider DA1 and DB1 the same and DA2 and DB2 the same, you can use their magnitude and the phase shift to calculate what is the RMS current, what is the average power that is transferred from one port to another. And as I say, this is really the simple case that you put them equal, and the waveform here on the right shows the voltage waveform, and then what would be the waveform of power and what would be the waveform of the voltage difference. One of the major tasks that we have always is to make sure that the power, if you transfer from left to right, for instance, it's always positive. So there is no negative power component, and that would be reducing your RMS current. If you want to transfer power from one side to another, you really should not have a negative power flowing from the other side. So for this case, you can formulate the RMS current. And RMS current, although it is complex, but it's kind of, if you go through it, it makes really physical sense of what it is. And then there are cases that the power, you want to just make sure that, again, your power value are positive all the time flowing, and it's not negative. So it's going to be RMS current. And with that, now I'm gonna pivot into looking at the few I'm going to look at the actual system implementation using the DAB. It seems that it's really early morning. I'm a bit slow here, but I have many slides to talk about, so I definitely have to skip several of them. So there are major challenges when you do high power solid state transformer design. One is, first is you have to minimize the leakage, so you maximize your power output. Second, you have to avoid saturation. And then you want to minimize your core loss, you want to minimize your copper loss, you have insulation concern, creepage distance, partial discharge, you have parasitics, you have EMI noise, you need to do shielding, and you need to design for that. You have thermal analysis, you have cooling, and you have to perform FEA simulation. Then you have to perform optimization. You have to build a prototype. You have to test all your the high voltage silicon carbide devices. You need to do gate drives and so forth. So it's kind of a combination of all electrical problems you can collect in a high power solid state transformers. So, and at the lower voltage and lower power, these problems, a lot of them go away. So what we need to do is look at, for the system, we look at transformer first, different core dimensions, sectional areas, transformer windings, number of windings, and then you want to do insulation sheets, you want to look at the core volume, you're going to look at the core loss and efficiency, transformer weight, and cost. So all of these, they come for the transformer, high frequency transformer analysis. High frequency transformer sits right in the middle, and you have a lot of trade-offs. Your Bmax is generally limited based on the materials that you get. For instance, for ferrite, you cannot go beyond 0.3 Tesla for the core. Then you don't want to increase the volume. If you increase the volume, your loss go down, but if you increase the volume, your weight goes up, cost goes up, and so forth. And then leakage, you want to limit the leakage based on the number of turns, and that impacts your winding length and then and your loss in the system as well. So our practical or our objectives to do projects here, one is a multi-port system. a multi-port system for this specific case can be connected to the grid, can be connected to the solar PV and energy storage and a load all at the same time. So this is almost a smart node that can transfer power in 4 ports and collect them all at once. It has the ability to do volt var and voltage support as well. And then, of course, you go through a complex process, as I mentioned, from the transformer design, from the converter design, from the topology. Then you got to go through all the creepage distance, insulation, and so forth, especially the case that you have a medium voltage. For this case, our medium voltage 4160 volt, 3-phase AC. And design of the transformer with many components, all the windings, all the sheets that go in between them, and of course, all the practical cases there. And loss analysis is the paramount in the designing. And we took the application that, of course, we want to minimize the RMS current, but then that minimizes the conduction loss and minimize the conduction loss in the transformer, as well as minimizing the conduction loss in the converter. So, what we have is now we have the switching loss as well as the transformer loss, and those losses are not included in the RMS calculation of the current. So for that, you really need to do another level of optimization to consider switching loss and to consider the transformer loss. And one way to do it is that you do simulation of the system with actual parameters. And what we do is we take our transformer, we design it, we take it to Maxwell 3D model, then we bring it as a co-simulation to Simplorer. We apply now switching. This is a in this model now, you can look at the transformer loss, you can look at the switching loss, you can look at all conduction loss. In addition to that, you can look at all the transients and what happens to your flux, and if you get saturation or not. And this would be really a good way of optimizing your system. This really comes almost as the last step after you do all your work for the design. So this shows a transformer. I don't have a good size indication here, but this is something that you can wrap your hands around it and just lift it. It's somewhere about 10 to 15 pounds of weight, but it's a 100 kilowatt transformer. It has 4 ports. Each port is 25 kilowatt. And so that just gives you really about the size, how you can make these systems small. And here you can see the systems put together, the experimental system with all the controls for 4 port, and the medium voltage end is, of course, it has to go away. This is really guarded out system. We put a transformer here. The transformer actually have to sit here, but for initial isolation concern, we put it out to test to the medium voltage, and the load really flows from the other side. And in a low voltage case, you can put the transformer easily in the system, which sits here, and you would have really 4-port system. These are all experiments that at various cases and phase shifts, you can really look at how you move the power, and then how you can control the power from one port to another. And you have here 4 ports of the system to transfer power. The second case that I was looking at was at the building block, and in the building block here, this can be used as a building block for any medium voltage system. So you can get 13.8 kV to 4160. This can be electric ship. This can be any distribution system. So one of the big tasks is really the design of the transformer. And I'm just going to move down to the design of the transformer, which really has is really complex. However, before that, one of the big cases that we have is the medium voltage. When you have high voltage in a system, like this DAB case here, this is the transformer primary and this is the secondary. You have to identify all the voltage differences and how you are going to insulation for different parts of the system, what the insulation levels are. If you don't ground the core, the insulation can be at 6.5 kV. And if you ground, then you have to move it up to 13.8 kV for 13 kV for the system. You got to look at all the leakage capacitances, and those leakage capacitances are going to introduce the EMI current that are going to, of course, have common mode noise, and you're going to have a lot of issues with the noise doing a 13 kV DC and then 20 kilohertz. So all those capacitances must be identified and reduced in the system to make sure that happens. So with that, you get the transformer design. And this transformer, again, the size is not significant, but the power and voltage is really significant for this transformer. We go through multiple stages of the design, as I mentioned, and kind of looking at the flux level, if you can control the power and what the leakage inductance of the system is going to become. Okay, so one of the methods to simulate this. Please mute if you don't want to ask questions.
Some feature of this app.
I am. So Professor Bolbol, if you can mute. Yeah, I do that here, so you can see participant where the noise comes from. Oh, but it's not still. So one thing is, first you start with simulating modeling. Very simple simulating modeling. You look at all your currents and how the system works. And then with that, you can get the fundamental idea of what your control should be and in ideal transformer case and how you can transfer power. The second is now put Simplorer. And when you put Simplorer—
By the way, Professor Nasiri, you have 5 minutes left.
And all the conduction loss for the system while keeping the same control. In the third stage, you go ultimate. You put Maxwell 3D, you put your actual transformer design in there, and with this, you can get all the losses in the transformer, in the switches, and conduction loss, and the full system design can be achieved using this case. The third case that I had for a DAB, and I want to introduce the concept here only, and this is a very interesting concept that you have, for instance, solar PV here on the right-hand side.
Professor Nasiri, sorry to interrupt. You have 5 minutes left.
Oh, thank you. I appreciate it. So you have DC power voltage coming in here, and the other side, you're going to have 13.8 kV AC. Your DC can be at like 1 kV DC, which is very common for solar PV. So how do we go about this? You can use a resonant solid-state transformer to do this. And doing that, you can directly go to the medium voltage and give several level of optimization. One is how you do this. This is a DC here. You put a DAB here. On the secondary, of course, this is diode bridge. We did not need this to be bidirectional, so we put diode bridge here. You put a resonance, series loaded resonant converter here with a capacitor in series. And then this voltage, you take it DC to take it to pulse voltage here. And since you make this frequency high, for us, this frequency is between 30 to 60 kilohertz. And you can change between 30 to 60 kilohertz. Doing that, we build a rectified DC voltage on this capacitor, a rectified DC voltage. And from here, we get 6.5 kV IGBTs. and run them at 60 kilohertz, 60 hertz only. So this is line frequency, 60 hertz, and then connected to the grid. Doing this, the switching frequency almost goes down to 0 because you have a 60 hertz switching. You can establish resonance here, and with resonance you can get zero current and 0 voltage switching for the devices here. Then adding the system, you're adding gain, meaning that you can deal with the system when the voltage goes down, so you can have extended maximum power point tracking for this system as well. This all sits based on a resonant configuration, and there is really a very interesting path for controlling the power between duty ratio and the phase shift. Of course, here we have only one duty ratio, not two duty ratio. And you can see the experiment case for this system here, built and all tested when you change the current of the grid from the low to the high, and then do that really through various steps, as I mentioned here, changing varying frequency between 30 to 60 kilohertz, then changing the duty ratio and changing the phase shift. So with all that, you get really an optimal case of a very small loss, very large maximum power point tracking range, and then you can also get very small size for the whole system and directly connect it to medium voltage. So with that, Professor Bolbol, I am going to go to my conclusions, and of course, I skip a few slides, one of the projects, but DABs are finding new applications for various compact and isolated converters. The major design complications are transformer, hardware control, and medium voltage issues. And then we discussed the DAB control and the transformer designs and some of the voltage issues that come with it. And then the processes to do model, to do simulation, and then to do experiments to, of course, confirm the results. With that, I give this back to Professor Bolbol for any questions that he might have.
Okay, thank you very much. Finishing in time and very good information. Professor Rosario, I think, is here. Would you like to come with us, Rosario? Okay, he's here. Okay. Would you like to collect the question if they have any? Please open your microphone.
Everybody can use the hand figure on the screen to ask the question. That means you are raising your hand.
Of course. Now I am ready to collect the question from the audience, but I think that we can see each other if there are some questions. If not, I have to.
Also, welcome, by the way, Rosario.
Welcome. Thank you for all. Bye-bye to all the organization, of course. Later on, I will connect with you, Ilami.
What a nice,
and all,
what a nice
and all guys.
I can see all my on the screen. Welcome.
Thank you very much. And thank you for inviting me by cellular, because I am not in my office, so I had some problem to connect. But now it's all okay. Hi, Adel. Very, very nice presentation. My compliments. I hope you will send to me this presentation, because I want to study it.
Well, thank you, Rosario. I appreciate it. Yes.
Any
definitely.
question from the audience?
Any question?
So I can begin. Adel? Yes, of course, Ilami. Ilami, I cannot.
Let me open my microphone.
No, you're muted, Ilhami. Now you're muted.
Yes. Switch on the microphone. Okay.
Yeah, it is on now. Okay. First of all, I really would like to thank you, Professor Adel Nasri, to deliver his good speech. Do you hear me?
Yeah.
Yes. Yes.
Kurukawa is trying to say something, but I don't understand.
Yeah.
Okay. I think he has a question.
Adel, yeah. Thank you very much for your interesting presentation. So I ask you, so the relationship between the switching frequency and new device, that is the SIC. Do you have any opinion?
Oh, absolutely. So, you know, switching frequency is not, frankly, limited by the device only. It's a lot of times switching frequency is limited by your system. So, meaning that if you have a 1200 volt silicon carbide device, you're able to switch it at 1 megahertz, or you can switch it at 2 megahertz. As long as I've seen systems switching 1200 volt switches at 1 megahertz, they proposed 1 megahertz, they had trouble, but they were able to do it at 750 kilohertz switching frequency. However, that was absolutely resonant circuit that you could minimize your loss. So switching frequency is mostly limited by the thermal performance. So how much loss is going to exist in the device, and then how you can take that loss out. If the loss is really minimized, you can move up. And I was absolutely impressed by this. There's somebody who has done this medium voltage, 750 kilohertz, the kind of solid state transformer. And but this is for 1200 kV devices. When you move up switching voltages, for instance, for 10 kV devices, 20 kilohertz is the maximum bound. It's, you know, you have to, of course, charge and discharge the gate at that frequency, if you imagine. And then with that comes a lot of dVe over dt and for the system. So the switching, kind of a good range for there is somewhere about 10 kilohertz, not beyond 10 kilohertz. We have targeted almost 20 kilohertz, which cannot be achieved, in my opinion, 20 kilohertz in the coming years. We have to stay somewhere between 10 to 15 kilohertz. For our projects, the highest switching frequency that we have applied are on 1700 volt silicon carbide devices and 1200 volt silicon carbide devices at 100 kilohertz. So we moved it all the way to 100 kilohertz a lot of time by reducing the loss on the device and make sure it just operates efficiently. You can go higher, but probably you're limited by the loss in the system.
Julio, switch on the microphone.
Okay. Yeah. Thank you very much. And so the transformer design is very interesting.
Yes, yes. Actually, this has been one of the works that we have been working in my lab, and really goes back long ago. We have spent a lot of time to become a powerhouse for the high frequency transformer. Yeah. So now we are looking at transformer low voltage to high voltage and frequency ranges all the way up to 100 kilohertz for transformer.
Thank you very much. Good presentation.
Thank you, Furio. There are any questions from the others?
Okay,
Eli, thank you.
Okay, I think I can ask now. Professor Nasri, I saw a good combination of the transformer and the different sources and load together. renewable energy sources, energy storage, batteries, and the other grid and the load together on one transformer at the beginning of your presentation. I wonder what is the frequency on the transformer? Is it fixed 50 hertz or other high frequency, or is it a mixed frequency coming from different sources? And then can you talk about it, please?
Definitely. So if it were 50 hertz, then there would be no reason for us to do all this. So definitely it's not 50 hertz. So far we built two systems. One was at low voltage that each port, there were three ports were at 400 volt DC, another port is at 800 volt DC. The frequency for that is 100 kilohertz. So 25 kV on each port. The second case that we have, we move one of the ports to medium voltage. So one of the ports is as 7.2 kV DC. So for that system, we are only at 50 kilohertz. And then because of medium voltage, really just being very careful, we moved it up and we pushed the highest level is 50 kilohertz for the transformer. And for that reason, really, the size is so small. That's why I mentioned you can. This 100 kilowatt transformer, you can wrap your hands around it and just, it's about 15 pounds of transformer in terms of weight. So very compact. Of course, you have to go with all the insulation cases. That's why the system gets a bit bigger. You saw the picture I had. Transformer was even outside because we were doing testing. Wanted to make sure we don't have any voltage issues.
So I want to make sure that you have the different frequency and the different voltage levels on the transformer. Is that correct?
All ports must be the same frequency. You cannot have different frequency. So frequency, all are the same. And the way you adjust it is there is duty ratio that you have, the voltage magnitude, and the phase shift. So with all these three parameters, now you have 4 ports, you get almost infinite number of combinations that you can do with the voltage value, the duty ratio, and the phase shift. However, we limited the whole cases to 4 cases to get the most optimized case. There are only 8 cases that you can get the best situation out of this. And in that 8, we optimized even further to minimize the RMS current that flows. And that would be really by you fixing either duty ratios or looking at the voltage magnitudes or fixing the phase shift or so.
Why I am talking about this one, do you know, Professor Nasiri? I think you can have different frequency and different voltage levels on the transformer from different sources. This is also possible. You can create such a system and then use this one for different purposes. I remember my PhD subject, which is the mixed frequency testing of induction machine. And then I supplied a voltage which includes different voltage levels, and each voltage levels have different frequencies.
Right.
And then I applied this one to the stator of the induction machine, which is similar to the transformer. And then out of that, I tried to run the induction machine like under load. Even there is no load on its itself, so it acts like a running under load and drawing sometimes high current from the system and then reducing the current. So that case will be possible in your project as well. So I can recommend you to try to create different voltage levels and different frequencies on the transformer. Maybe you can obtain different possibilities there.
So I'm showing here the schematic of the system, of course, the 4-port system. The way is working is, of course, all surrounding is DC, and then we have DC to AC here, except for the load end here, which is a rectifier. if just controlling the current of each port at 100 kilohertz and controlling the flux, for this case, which was really 50 kilohertz, it's really cumbersome. You want to control the flux, make sure your transformer doesn't saturate in transient when you're doing 50 kilohertz. And transient here means a steady state, meaning if each cycle you saturate a transformer, you will saturate it at 50 kilohertz frequency. So that's not going to happen. I mean, that's not going to be practical. So doing it at a single frequency, it's really challenging, extremely challenging, especially when you have 4 ports and you have to control the flux in the core. I really don't know if this is, we can do anything with variable frequency. If you say the frequency here and here would be different, I think it would be almost impossible to control the current because the frequency is high. If you're 50 or 60 hertz, yes, you can control the current. But when the frequency goes up, your control goes away. You cannot really control the current. That's probably why I'm a bit, not optimistic about it.
Okay. Okay, I understand. Thank you.
Thank you. Any other question?
One more person, Erdal, I think.
Morning, Professor Erdal.
Yes. Thank you for your nice presentation, Professor Naseri. I want to ask you a question about what can you say about core losses of high-frequency transformers?
So of course, core loss is just main issue when you do high frequency transformer design, right? The various loss that exist, eddy current and hysteresis. So mostly what we have done is we went based on the core materials. So we look at the core materials, and then based on the pH curve of manufacturer, we look at really what the loss would be, and we really moved a lot about what core we use. So at the high frequency, for instance, when you go above 20-25 kilohertz, there is no other choice but ferrite. And when you go at the lower frequency, then you can use nanocrystalline materials, which are quite expensive, but their loss is really small at mid-range frequency. When you have frequencies somewhere between 5 to 15 kilohertz or so, then you can use met glass materials, which are probably good about 10 kilohertz or so. They are a cheaper material that can be used. And of course, the loss, the way we do the losses, we insert the pH curve of the transformer into our model. And since these systems are really very transient systems, so you're even when you switch, your current sometimes go full scale, sometimes it doesn't. And meaning that your system is in transient status all the time when you switch at 50 kilohertz or even less when you're doing at 5 to 10 kilohertz. So for that reason, you really need to have a very accurate modeling of what the I have been muted all the time.
Okay. No, just now.
Okay, I'm sorry.
Nothing is missing.
Okay. Did I answer the question with while I was mute or no? I was on mute.
I think you answered the question because
Thank you.
I muted all of you because there was a voice coming from somewhere, so it was my mistake. So I think Rosario, there is one hand raised.
I think we should take the last question. We are running out of time.
Yeah. Brahima is there.
Okay, do you hear me?
Yeah.
Okay, Professor Nasri, thank you for your very interesting presentation. And I have a question tied to the resonance converter. When you use a resonance conversion, you have to master the leakage inductance, because your frequencies, you told that the frequencies must be the same on all the converters. And how can you master the leakage inductances over the transformer? Because it has an effect on the resonant conversion.
Right. Thank you for the question. This is actually a great question. So for our case here, for the resonant converter, actually we needed the leakage inductance. So a lot of cases you try to minimize the leakage inductance to increase the power transfer. But for us, we designed it for a specific leakage inductance, for this case, 4 microhenry for the transformer. And then you do the leakage inductances, there are several ways that you design for it. And then you want to design for it and then do kind of FEA analysis, make sure you get to the range. And of course, when you get the transformer with all the manufacturing cases, you're going to get a different range for your leakage inductance. So what really impacts is the number of turns, that of course that you can fix. However, the dimension of the winding and the distances between primary and secondary winding, and then the winding to the core, those impact the leakage inductance. We actually design for a specific distance. We put a spacers between winding, and then we try to kind of compress the winding, make sure that the space is maintained. It's not being loose or anything. I can actually show you a few pictures that we kind of insert spacers in there to get to a specific leakage inductance that we want. And then, so what we design is for a 4 microhenry, for this specific case, we kind of design the resonance for two things. Then we have another series capacitance that adds, of course, to this capacitor resonance. You cannot change that, and it could be different. What we had was we kind of have the variable frequency case as well. So, of course, when you design the system, there is under resonance, there is resonance, then there's beyond resonance. We operated the system at beyond resonance. And to do that, to get the zero voltage switching, we went beyond resonance. And then we don't get close to resonant frequency. So you can stay 10, 20% above the resonant frequency and operate your system above that range. And then with that, any variation that you get for your inductor, your transformer leakage inductance, as well as your capacitor, then you're immune from that. So you never get close to your resonant frequency and you stay above that. So we operated in a super resonance case of the 3 region that we have. That's kind of how we protect ourselves.
Thank you so much.
Definitely.
We have enough time to another question. Ilham, do you think that we have time or not?
I think we are over time, so we had to stop it 15 minutes ago, but there were very interesting questions. So we should stop now and then give 5 minutes to prepare the second.
We will give the certificate.
Yeah. Now certificate time.
Okay, we will share our certificate.
Then we will collapse.
you very much, Adel. It was very interesting.
Definitely.
Is it sharing now?
Yes, thank you very much.
Congratulations, Professor Adel Nasri.
Okay, we are closing this section. Thank you very much for Professor Nasri and audience, for everyone. Thank you. Thank you very much.
Now
Thank you very much.
pass the stage to Adel Nasri and Thomas.
Adel, thank you for all.
Excuse me. Now, I think the Professor Adel Nasri and George Thomas are the session chairs. Please take the stage for your session.
I will empty my seat for Dr. Nasri.
So I suggest Professor Thomas go. Is he here? And
I think he is in. I think Thomas. Let me see.
Let's see.
Thomas, yes, he's in.
Okay, I don't seem to have the bio for
George, Thomas, please. Is Thomas hearing me?
この辺だとやっぱ横向いてる感じします目線。それがちょっとですね。Thank you very much, Professor Najiri and Professor Thomas.
Yeah.
Ilhami.
Yeah, you can.
Yeah, you need to unmute your microphone, Professor.
I am on mute. I think you can hear me. I don't have the bio
You
for.
are okay. You are okay. But
Yes,
I think Professor Thomas has some.
I don't have the bio for our next speaker.
Bios in booklet, Professor Nasri. You can find the web page. Yeah,
sure.
Did you find it, Professor Nasri?
I am trying. Hold on one second. I think you sent the.
It is on the website in the booklet, main page.
I can send you, Professor Nasri.
Okay, I think I see it here now. That's not it. So it's your draft booklet. Is that it? Maybe it is. Okay, I have it. Yes. Is Dr. Kawagachi is the next speaker?
Yes, yes, please.
Yes. Okay. Everyone, I'm sorry. I was, I was a bit sleepy probably. That kind of mixing up. Our next speaker is Mr. Akira Kawagachi. Mr. Kawagachi, the topic of his presentation is contributions to sustainable future through PIE, power electronics in everything. And Mr. Kawagachi is currently the Vice President of TMEIC in Japan. He has a long career in industry and with focus on energy systems and energy conversion. And he was the senior manager of power electronic department at I think the same company. What I have is, yes. He was in Mitsubishi Electric Industrial System since October 2003. And he is Vice President of Power Electronics System Division there. And then before that, he served as Deputy Vice President. He served as Technology Executive. He served as Senior Manager of Photovoltaic Systems Power Center. He also started with Senior Manager of Power Electronics Department. So with this long career in power electronics and in energy system, we are really delighted to have Mr. Kawagachi, and I'm really looking forward to his talk again, which is titled Contribution to Sustainable Future Through Power Electronics in Everything. So Mr. Kawagachi, if you please can share your screen. So,
can you see my screen? Well, it's not yet shared.
Yes,
it is.
Yes,
it is.
we can see your screen.
Oh,
yes.
Okay. Okay. So, could I start right now? Well, thank you very much.
Yes. If you have a slide deck, you want to show that. Yeah.
Yes. So, it's not on screen yet.
No, not the slide deck. What you were showing your bio 1 second, and then it went away.
Oh, okay. I'm sorry. 1 second, because it.
Sure. You got to make sure you just share your desktop or at least PowerPoint.
Okay.
In the middle of the section there is share. You can share.
Yeah, share. Again on the end. Is it?
Okay.
Okay.
Okay, it's coming.
Yes,
Yep.
Perfect.
Okay.
Very good.
Okay, thank you very much. Sorry, because this is our first time to use this team.
Definitely, yes.
The software. But actually, this is very exciting to talk. All the guys all over the world. So I don't know. I need to say good morning or good evening or
both.
Okay, both. Yes. Thank you very much, Professor Naziri, and thank you very much, Professor Dakyo, Professor Kolak, and Professor Kurokawa. My name is Kawaguchi. I am from TMAC Japan, yes, and Professor Naziri kindly introduced me. So my life is all the way with power electronics. So it is my great pleasure to be a keynote speaker of this prestigious conference, Icsmartgrid Virtually 2020. We are so happy and proud that this conference started totally successfully, overcoming the COVID-19. And I'm so excited to join the session online from Japan here, thousands of miles away from Paris. So today, in this speech, I'm presenting the contribution to sustainable future through the concept of PEIE, power electronics in everything. Well, so in the beginning of my presentation, so I'd like to convey a message from the honorary chair, Mr. Kikuchi.
Yes, you can go. I can take over your role.
Mr. Kikuchi, who is the senior vice president of our company. So he would like to show his great respect to those who organized this digital conference, overcoming COVID-19. To get the general to the general chair or the general co-chairs and all the chairpersons, all the committee members, and all the staffs who prepared and manages this excellent conference on the web. He very much thanks for invitations to the honorary chair as one of the representatives from industries. He hopes that this conference will be very successful with constructive and creative paper presentations and discussions. So here, I just want to briefly introduce our company, TMIC. So TMIC is a young but experienced manufacturer playing globally. So we are developing, designing, and manufacturing industrial systems and products. So we are excellent in large capacity power electronics for industries. High quality products based on Japanese practices is one of our features. TMIC was established in 2003, merging industrial systems manufacturing part from Toshiba and Mitsubishi Electric. Before coming at TMIC, actually, we have been doing these businesses in the two companies for a long time. So that's why we TMIC are the young company, but also a long experienced company. So we are the technology-based company, and our core competences are engineering and manufacturing, power electronics, and rotating machineries. So we have 4 manufacturing bases in Japan, our country. So for power electronics, we have 2 in Fuchu and in Kobe. So actually, I'm presenting today from Fuchu factory. And for rotating machineries, we also have 2 in Keihin and Nagasaki. All those factories in our manner are basically the mother factory of each industry. We ship out the product technologies over the world from the mother factories. And we TMIC have 5 global manufacturing bases, 1 in the United States, another in India, and 3 in China. In all the manufacturing bases, we are manufacturing and supplying power electronics. Against COVID-19 these days, from March, it has been very difficult time actually. Maybe you all too. The situation was quite different country by country. Maybe the older part will be starting over these days, but still have very many, there are so many difficulties actually. Most of you who is joining to this conference may know how greatly the technology power electronics contribute to the industry. When you want to do something new or something innovative, you need a power electronics in these days. PEIE, power electronics in everything, is our concept and will further contribute to the sustainable society with more power from renewables, more stable power to digitalize the world, and more energy efficiency in industries. And CO2 abatement is one of emerging global issues. renewable and end-use efficiency are expected to play the most important roles in CO2 abatement. A TMAC technology enables to contribute to solutions to the challenge of global scale. There is no doubt that power electronics is a key to world future energy. Today, I'm going to present along with those items from generation, grid and transmission, conversion, and then efficient energy usage. These days, another new topic is raised: the contribution to business continuity plan by stable and efficient power, and new ideas for backing up the power system. These are the lineup of power electronics solutions in megawatt ranges: PV, ESS inverters for renewables, UPS, MPC for highly reliable and power source, and motor drives for efficient energy usage. From next section, I'd like to present for each applications. So these days, one of the most famous and important power generation is again renewable. So regarding the CO2 abatement, especially renewable energy is playing important roles. The large capacity PV inverters. Essentially, the inverter converts the DC power output from the panel to AC power. These days, large capacity PV inverters, called as a mega solar plant, sometimes generates more than 100 megawatt power, the very huge powers. Now, these large capacity inverters are manufactured all over worldwide. If you need more power from the panels more efficiently, you will choose higher DC voltage. As the generation share of PV plants increases in the AC power network, the inverters now start playing important roles, such like to stabilize the distribution line voltage. With the world's highest conversion efficiency and control performance, the TMAC PV inverters are contributing to generation power increase. Deliveries more than tens of gigawatt experiences all over the world. The DC output of the PV panels are connected to the collection boxes, then connect to the inverters, converted to the AC power. Connected to the AC power network through transformers and high voltage distribution panels. Those are the basic function of PV inverters. And this slide shows the outline of the large-scale capacity outdoor inverters, in this case rated 3.2 megawatt. So convert its power very efficient, like 98.9%. So just 1.1% losses, including the auxiliary power to maintain the operation of the plant inverters. So the entire system, it's a very, very efficient. And one of the most important functions is the MPPT, maximum power point tracking function. The power output depends on the operation point choices. Enables to harvest more and more power from the DC solar panels. So you should carefully choose the inverters by checking its performance of MPPT functions and its effect for you, how much power you can earn from the same DC panels. TMAC PV inverters contribute to increase the generation power from the PV panels with high MPPT efficiency and high conversion efficiency. So product lineup shows the history of technology. So one index is DC voltage. So from its beginning of mega solar, it was designed and started from DC 600 volt or lower. And nowadays it counts 1000 and now 1.5 kV. And regarding the installation, it has changed from indoor type to outdoor type. Enables direct installation to the site and saves the works on site. So here present the concept of the universal PCS. That's a new product of ours, and that is individual modular inverter design. Enables higher availability, easier maintenance, multiple MPPTs, enables high reliability, high efficiency, and long life and safety PV system. Those universal inverter design concept, highly modularity gives you the big benefit. It is high efficiency for power and high availability for energy. The modular design enables to limit the loss of power output at the contingency and to shorten the repairing time. Then loss of energy will be minimized. It's easy to understand that who installed the solar panel wants to earn as much power as he can harvest from the panel. It is very important to minimize the generation losses. That means you can get the maximized power energy availability. So this yellow graph shows the differences of the modular design.
Excuse me, your screen is not visible to us.
Okay.
Can you share your screen, please?
Now.
Yeah.
Okay, so there are some time lags to change the pages. Okay.
Yeah.
Well, I guess I am indicating, I'm showing the page 24 with two yellow graphs. Okay. So this graph shows the difference of the modular design and the conventional designs. So clearly indicates that the generation loss is minimized by modular design. And the modular design enables various combination schemes. The modular design minimizes the requirements for the landscape. It gives you the flexibility of the installation designs. Installing outside or even installing inside the containers. The modular design minimizes the restriction for transportation to site. As this picture shows, so you can use small trailers to the site. And this year, so we got an award from Frost & Sullivan. It's an American company, American research company. And we've been awarded from 2014 for 5 consecutive years for our activities in industrial power electronics field. And this year, the universal PCS concept was one of the big reasons for the nomination of the award. Could you go back to the last one? So in some picture, maybe you can find my picture in TechSheet. Okay, next reference. Now I'm showing the page 27. So in order to increase the generation share from the renewables, the ESS, energy storage system, are necessary. So energy storage systems also contribute efficient energy management in industries. Essentially, its function is stabilization the power of renewable energies, averaging or shifting of its peak is also important. No energy is generated from the ESS system itself, so the efficiency of the system is also very important. Now change to page 28. As the generation share of renewables increase in AC power networks, the power frequency variation increases due to power variation increases from renewables. Energy storage system, ESS, are promoted to stabilize the frequency by absorbing the power variation. TMAC inverter marked the world's highest conversion efficiency. We have many experience of deliveries to large-scale projects of tens of megawatt or megawatt hours. And in page 29, these are the example of the product lineup. From 100 kilowatt up to megawatt sized inverters have been thrown into the market. So this wide range lineup of various system requirements. Continuous development for new product is necessary to give solutions to those changing requirements from the field or from the customers. And page 13 shows the modular design can also be applied to the energy storage system with battery banks. So universal PCS inverter consisting of plural inverter modules are connected to the power grid through transformers. And page 31, this slide shows the PV and ESS hybrid systems. So inverter modules can be operated as a PV inverter and also as the ESS inverter. The modular inverter's design makes it easier to construct the hybrid system with PV and batteries. The combination of module numbers for PV and for ESS has flexibility and can be optimized as required. And page 32, in order to increase renewable power in power grids, the advanced stabilization control systems are essential to coordinate between the varying generations and varying consumptions. So in this presentation, power plant controllers, PPC, and some proposals of the control for solution are presented. And page 33, the power electronics inverters for PVs and the ESS can control both the active and reactive power. The power plant controller, PPC, supervise the PVs and ESS to realize the functions to stabilize the power grid for various purposes. By controlling the active power, inverters balances the generations and consumptions in a power grid and stabilizes the frequency. By controlling the reactive power, inverter stabilizes the grid voltage. The power plant controllers are provided for various purposes, managing those active power and reactive power controls. In page 34, some very typical operations are listed here. The short-time range control stabilizes the energy fluctuation. The long-time range control can shape and shift the load connected to the grid. ESS can support grid stability by compensating the output power variations from renewable generations, PV, wind turbine, and etc. ESS can shape and shift the load connected to the grid. It will balance the generation and consumption in the grid. So page 35, the power plant controller PPC controls the power from the renewable generations and the ESS according to the commands from the power distributor and monitoring the site meter. Active power controls are listed here left. A site power limit control, ramp rate control, site frequency controls. And reactive power controls are listed right. Voltage control, power factor control, and nighttime power limit controls as well. And page 36, for ancillary service solutions, power plant controller also plays the very important roles. Manage total system following power meter, for example. A frequency regulation, voltage support for network system. ESS with power plant controller enables to support block starting, spinning reserve, and other controls. So even in these ancillary service solutions, the power plant controller plays very important role as well. On page 37, so the requirements to the power grid stabilization varies case by case and time to time. The optimized controls are proposed according to local grid codes and the customer's requirement. Sophisticated power grid simulation technologies these days are essential to propose the optimized control system. On page 38, this map shows the control technologies for power grid stabilization. I think very wide range of the time second up to time or days, and local to the power grid, the very wide range of control. So solutions are proposed based on the various control technologies. Fast response control can be proposed using power electronics, inverters for PVs, and ESSs, like red dotted squares. And in page 39, optimized systems are proposed based on the simulations with the de facto software, sometimes just focusing on the inverter itself, or sometimes focusing on the entire system, including the power plant controllers. Sometimes precise modeling of the transient phenomena like a small time-wise, or sometimes long time range total power flow control, etc., or will be simulated. Okay, page 14. So when we talk about the power system, so these days, we need to talk about the two topics here in Japan. In page 41, so one is a very big topic that covers the entire world and even affected on this conference, but it's COVID-19. The keyword is telework that gave a drastic change on energy, on every single business field. Emerging demands for information, communication, traffic, and digital devices, and high requirement for power system as well. And in page 40, the other is extreme weather. These years here in Japan, we have an experience of earthquake or very heavy rainfall or typhoon. That's resulted in long-term power outage, power losses for weeks or even for months. Now we need to start discuss about how to construct a power system, just like microgrid or BCP, business continuity plans. A wide range power grid which experienced very much difficult to start over after those shut down. Page 43, UPS supports remote works, online meetings, and contact tracing applications. Also, the data center, which allows the large capacity communications. So, that is armors against COVID-19. The UPS contributes to the digital facilities, including large data centers, by supplying electricity without any interruption. Large capacity, high efficiency, and high reliable UPS technologies are required here. On page 44, this is overview of UPS. The UPS supplies the power without any interruption to the application fields, which is socially very important. Normally, power is fed from AC power network through converters and inverters to the important loads. In case of any interruption of the AC power network, battery will take over the power sources. Page 45, the power consumption in data centers is one of energy issues in the world. More efficiency is greatly required there. High efficiency UPSs are required in addition to high reliability to feed the power to the digitalized world. Page 46, the power usage effectiveness, PUE, is one of the keywords describing the trends of power consumption. In the data center applications, the index of PUE, power usage effectiveness, continues to improve. Although the improvement of the efficiency in UPS that keeps the power consumption in UPS to almost same constant level. In page 47, large capacity, high efficient UPSs are available responding to data center power capacity increase realized by advanced technology. High reliability can be realized by redundant system configuration with plural UPSs connected in series or in parallel. Even one of UPSs failed, the redundant system continues to provide the power to the important loads and continued power source. The page 48, the COVID-19 introduced the new keyword such as the remote works into the production of medicines and vaccines. The power supply have to support those very critical and sensitive loads and contributes to our society fight against COVID-19. Suppose page 49 shows the MPC stands for multiple power compensators. Normally supplies the power through high speed switch in high efficiency. In case of AC power failure, high speed switch cuts off the AC power network to protect the load and feed the power from the battery to the load through inverters. Total capacity of the system is rather bigger than UPS. Sometimes it covers almost all the function of the factory. On page 50, in the factory, there are some very sensitive facilities. MPC is rated at several megawatt and can feed the power to whole factory during a contingency in power network. MPC contributes to continue operation of the manufacturing process and prevents its shutdown. Consequently, MPC prevents large production loss and keeps the quality of the ICT devices manufactured there. Page 51. Normally, the MPC feeds the power to the factory directly through the high-speed AC switch. In case very sensitive loads are connected to the system, sometimes a very quick cut-off is required. The high-speed semiconductor switch will be applied, and the mechanical switch offers the cut-off time, typically 1 cycle, but utilizing the high-speed semiconductor switch offers the several milliseconds cut-off time, the very quick cut-off, and no effect to the load from the AC power network. So page 52, this slide shows lineup of MPC in megawatt scale. The megawatt scale factories are normally connected to those power lines in voltage 6.6 kV or 3.3 kV in Japan. Of course, the voltage depends country by country. A wide range of MPCs are available. In page 53, in these years in Japan, and again, I need to say that we have had experience by the extreme weather or earthquakes that hits the big damage to the power systems of the factory. It has been considered that the power system is very reliable here in Japan, and user has to prepare for just a very small power loss to protect the productivities in a facilities, like several 10 milliseconds or something like that. But it was noticed that hours or even days of our lives without electricity will be happen by the big damage to the power systems. So now users have to change their mind and change the philosophy of their preparation. In page 54, so right after the outage happened, so device like an MPC is useful. After that, in case still outage continues after the MPC runs out, then long-term power source devices like an emergency generator, we need to start it up and take them over the function. So it is very important to perform the cost-effective and also the very long-term ready power source system. That's a contingency plan. Okay, and page 55 and page 56. So my speech comes back to the shield abatement. Well, now some talk about the motor and its drive. So motor consumes 53% of the global electricity. The major part is found in industry. Higher efficiency of motor drive system in industries is essential for the sustainable future. Page 57, in industries, many motors are working and consuming much power. The combination of high voltage motor and the drive system contributes to extend energy efficiency in large machines in industries. TMAC features medium voltage drive inverters rated at several kV up to over the 10 kV with advanced technology for high voltage motors. Extra large drive inverters rated at tens of megawatts for replacing the gas turbine drives. Page 58 shows the very basic configuration of the motor drive system. The combination of large capacity motor and drive is applied to the applications. Steel mills, plants, and gantry cranes, and pipeline pumps stations. For large capacity applications, the high voltage motors offer high efficiency since they operate with small current. Further, they expand the energy efficiency in high voltage motors. High voltage inverters are essential. Page 55 shows the lineup of the high voltage drive inverters And those high voltage drive inverters promote further energy efficiency in the industries. The application fields are very wide, like written here. In page 16, this slide shows the configuration of the high voltage technology for series connection of cell inverters. That covers more than 10 kV inverters. The coordinated control technology for multiple cell inverters. Advanced cell control technology is necessary to realize high voltage and large capacity drives. Page 61, it's very important to design the combination of the motor and the drive system. Wide variety of the product gives you the wide variety of the applications in industry field. The combination of products from TMAC factories contributes more energy efficiency. So we manufacture high efficiency motors, high voltage, small current motors, and plus high efficiency adjustable speed drive gives you solution with more energy efficiency. Sorry, I'm just over time, but to summarize my presentation, I just want to all of you who joined this session and stayed until this very last slide to remember the word PEIE, the main concept of today's presentation, power electronics in everything. I presented PE, power electronics, in renewable generations, PE in power grid and better stability, and PE in digitalization for stable power supply and supporting fight against COVID-19, and PE in BCP for durable and resilient power supply, and PE in industries for higher energy and efficiency. Thank you very much for your attention, and thank you. This is all for my presentation.
Thank you very much.
Thank you very much. Really appreciate.
Okay, appreciate.
Yeah.
Do you hear me?
Yes, I can hear you, Ralph.
Okay, thank you for this very interesting presentation. I am Abdou Tankari from University of Paris Est. I replace Professor Nassiri in this chair. So the question is open. If there are some colleagues that have questions, you can raise your hand. You have in the middle of the screen, you have the hand, so you can process a question. Okay, Professor Dakio, please. We don't hear you, Professor Dakio.
Okay, now I think it's good. Okay, thank you so much. And for your presentation, it was very nice. And I want you to go back to the page 20 you showed us. Yes, page 20, please.
Yes. Well, wait a second, please.
Please, you can share. You can share the screen, please.
Yes, yes. Sorry.
I don't see nothing yet.
Can we share?
No, I don't have the screen.
Not yet.
Not yet? Oh.
No.
I think it's
okay. Could you
a page
yeah,
in which you showed the efficiency.
Yeah.
No, it's not this one. Yes, this one. 20.
Okay.
Okay. Okay, you showed the efficiency of the converters, right? And then if I look at the power ratio, the load in percentage, I think that 100% is a rated value of the load.
Yes.
And why do you have the maximum efficiency near 40% and not 100%?
Yeah, that's a very good question. So, so this data is rather, old. It was in the, days of we are designing the 100 ratio. Okay. Well, but please see that the difference of the efficiency in 100% and even for its peak, it's just 2% or something. So different, 0.2% or something. It's very small. Okay, and it depends on the circuit configuration or design. So I think it's the top. It's a little bit lower. So well, it's a beginning. We designed intentionally to make it the peak at 60% because every day it's not sunny, but sometimes cloudy day. So the total average sun radiation is 6% or something. So we try to design that peak at that. But these days, the most of the site of the PV is now overloaded. So the most of the time inverter is operated in 100 kV. So it's very important to focus on the 100% efficiencies.
Solution with there is no solution with the modularity principle on your converters?
Yes. This slide is not the modularity, but this slide, so other slides, this one, so central point type, like 3.2 megawatt type.
Okay. Thank you for your.
Thank you very much, Mr. Dakio.
Okay. Thank you, Professor Dakio. Another question from Sadek, Mohammad Sadek, please.
Your microphone is not on, Sadek.
You hear me?
Yes.
Yes.
Can you hear me clearly?
Yeah.
Very clearly.
Okay. Thank you very much, and really appreciation for your presentation, Mr. Kawaguchi. I don't know which slide was it that you said the controllative by the controlling the voltage, right? And this controlling is this is important actually for the modern society in the DERs which we use in the microgrid. But you don't speak about how could control the power, the real power by what? How could you explain that? No.
So actually, in my presentation, I didn't mention about the control scheme of those controllers like reactive power, active powers. As you mentioned, so the microgrid is very important right now, and yeah, sometimes the virtual synchronous generator control or those kind of control is also very important. And
so
the wide
this, I'm sorry.
Sorry,
I'm sorry
okay.
to interrupt you. Okay, I'm sorry to interrupt you. Is this the controlling of the power power active and reactive is a local control for the DGs or the bus actually connected with the bus in the main controller? Which one?
It depends on the system. Sometimes the controller is focusing on the voltage of the network point. It depends. Or sometimes it will be performed by the combination of the PV plant or wind turbine. In that case, we will focus on the power output of each device. So it depends on the system.
Okay.
So what is the control target?
Okay.
Yeah.
Thank you very much, sir.
Yeah, thank you very much. It's a very good question.
Okay.
Thank you.
Thank you very much. Professor Fujio, please. For your questions.
Thank you very much. Good and interesting presentation, Mr. Kaguchi.
Thank you very much.
Good. So, my question is many high power capacity PV inverters and so batteries are connected in the AC line. So
Yes.
in this case, how many voltage are changed due to fluctuation of solar cell?
You mean you're talking about the voltage change of AC lines?
Yes.
Well,
a large capacity solar cell are changed. So because the output voltage and the output power are changed.
Yes.
By the solar cell. So my question is, how many voltage are changed in the AC line after PV inverter?
Yes, it's very difficult question because it depends on how strong or how weak the system is, or how local the generation site is located.
Yeah.
So and actually, like in north area in Japan, it's a very good area for wind turbine and even for the PV. We are now right now very much very many generation site, and that is now leading the very big voltage flickers on the lines. Sometimes it's over than several percent or even for the 10%. So now it becomes a very big problem of those local areas. It's very many generation stations, but it's also very far from the its route line.
Yeah.
So yeah, station suppressing its fluctuation is very important.
Yeah. Okay. So the rule of electric power is very severe in Japan. Yeah.
Yes.
Thank you,
Yeah, thank
Professor.
you very much.
Okay, thank you very much, Professor Kurokawa. Professor Kolak, please.
First of all, I'd like to thank you for the nice presentation of Mr. Kawaguchi. It was very interesting and it is really in my field. I just wonder what is the biggest power of the inverter you are producing now?
Oh, it's a good question. Well, actually, it depends on the applications. So we are now manufacturing
3.2 megawatt you sent recently, or bigger than that?
Yes. For the PV inverters, 3.2 is one single inverters. Also, we actually consist of the combination of the universal PCS. In that case, the 1 unit is more than 5 megawatt. So
more than 5 megawatt.
Yes,
Okay.
yes. So the 1 unit is 5 megawatt. And regarding the power electronics, like motor drives, so we have manufacturing several tens of megawatt or more.
Tens of megawatt. Okay.
Today I didn't present it, but we are also manufacturing the converter for the transmission. In that case, several hundreds megawatt converter we are manufacturing.
Okay, very good. Thank you very much. Thank you.
Yeah, and Professor Korak-san, so this time I miss you. We could not meet again in France.
I'm planning to come over there to Japan, and then I asked Kurokawa to arrange an appointment from you and to visit you in your office.
Okay. Thank you very much.
Okay.
Okay. Thank you very much, Professor Cholak. So I have just a question about the MPPT. You showed that it's very performant, near 100%. It's very, very performant. That you know that in MPPT there are some constraints such as fluctuations of the power from wind turbine, in example, such as the performance and efficiency of the conversion of the power electronics conversions, and another is the performance of the control. So how about the strategy and method of control that you use in this system to have an efficient MPPT?
Mainly it depends on its control. Because this is a key to utilize the DC panel most efficiently. So mainly we control the DC voltage of the DC panel to harvest as much as power. And in case if you fluctuate the voltage to find out this very good point, that gives you the flicker to the, sometimes gives the flicker to the AC power. So you should be very careful to design.
Yeah, it's very constant.
Yeah, and to tell you the truth, actually this technology was established almost 20 years ago when we were designing the residential small PV inverters. And then we applied the same technology to this mega solar scale. That means it doesn't depend on the hardware. But I don't know it's applicable to the wind turbine or something like that. It's just for the unique technology of the PV inverters.
Okay, thank you. So just last question about the MPC. You use storage in case of collapse.
Yes.
So how you design the capacity of this storage, because the performance depends to the duration of the collapsing and the power of the global system, the energy system, and the power need in this situation.
Yes, that's also a very good question. So, so we are designing this MPC's storage, for the capacity of 1 second or something, very short.
Okay.
Sometimes we apply the lead acid battery, or depends on the customer's requirement, but sometimes we utilize the lithium-ion battery. And also it's not so long, so we can apply the capacitor for this storage as well. But as I mentioned, so these days some things have changed for the business continuity plan. In that case, we will install more more battery to stands for the longer duration of our outage.
Okay, thank you very much.
Okay, thank you very much for your question.
So, did you see my screen?
Yes,
Yes, we can see.
Okay,
The
it is your
certificate is on the
certification.
screen.
Thank you. Congratulations. And thank you very much for this interesting presentation. Very interesting topic
Yeah, thank you
and
very much.
application.
Excuse me, we have also another one for the teammate. I think Ramazan Binder can share it. Or I can share it. Ramazan, can you share it?
Not yet.
We have one certificate for the teammate.
Thank you very much.
Hold on a second. Can you see my screen now?
Yes.
Okay, this is outstanding contribution certificate presented to Toshiba Mitsubishi Electric Industry System Corporation as being the diamond sponsor for the International Conference on Smart Grid held at Paris, France, June 17, 19, 2020. Thank you very much.
Thank you very much. It's an honor.
This certificate will be sent to your email, Mr. Kawakuchi.
Okay, thank you very much. So they will be printed and will put on my wall in my room.
Sorry, we are all digitalized this year, so there is no hard copy.
It was very exciting.
Maybe this pandemic opened new business for all companies, including the email.
It's big change.
Okay. Ankari, I think we have already completed the morning sessions. There were two keynote speakers. You can close if you want. If there is no other question, you can close the session till 1 o'clock.
Okay. Thank you.
Okay. Thank you. Thank you very much.
Thank you very much.
See you at 1 o'clock.
See you soon.
Thank you very much. So, see you later.
See you later. Yeah.
Okay. See you later.
Okay, see you.
We will meet in the cafe room.
Okay.
We are going to have a coffee, of course.